This video is a demonstration of signals on pins causing interrupts on an ATtiny 3224 microcontroller. We will see that this works on the ATtiny very much like on any other Arduino device. We'll see what happens when interrupts are signaled at the same time and measure how many interrupts the ATtiny can process per second while running at 20 MHz. ATtiny software will display interrupt counts on a small OLED display that interfaces via I2C to the ATtiny. And we can watch signals on an oscilloscope. First, let's take a quick look at the software. Then we'll see the system in action. Here's our software for today. We're running the Arduino 1.8.19 IDE. And the first thing we see is that we're using a library. This library drives a small OLED display on which we can display the counts of interrupts that we'll see later on. And so first we declare some pins. The first two pins are the ones that signal the interrupts. So on the rising edge of signals on these pins, an interrupt occurs. The next two pins will be toggled in response to the interrupt, so we can watch the interrupts being serviced on an oscilloscope. And the first thing you need to do interrupts is interrupt handler functions. And we have two of them, one for each of the interrupt pins. And they're both going to count the number of interrupts that occur. So I've allocated variables for that purpose here, and notice that these have to be volatile. And that's because the main loop is also going to read them. So interrupt variables that are communicated between the interrupt handler and the main loop should be declared volatile. So here are our two interrupt functions, ISR1 function and ISR2 function, and they both do the same thing. They just keep a count of the interrupt, and then they also toggle a pin, but they do it in different ways. This first one is using something that's ATtiny specific. By writing 8 to register port B.out.tgl, we toggle pin PB3. The value 8 is because it's the third pin in the register. The second interrupt service routine is more conventional. It's doing standard Arduino. So it keeps its count, toggles the value of a state variable, and then writes that variable out onto the digital pin that we can see on the oscilloscope. Next, we'll scroll down and look at setup. And the first thing that happens there is that we initialize our OLED display. 128 by 32 is the pixel size of the OLED display. And here we're using an 8 by 16 font. So using this OLED display library is very easy. It's the same on an ATtiny as it is on any Arduino. And next we declare some pins. So these are our two input pins. So the signal on these pins causes the interrupt. And these are the two pins that we toggle in response to the interrupt. And then the next thing to do is to attach an ISR handling function to the interrupt pin and then declare that the interrupt will happen on the rising edge of the signal on the pin. And we do that for both ISR1 function and ISR2 function. And then for reasons we'll see, we disable interrupts. But all of this is absolutely standard Arduino. So one takeaway is that using interrupts on an ATtiny under Arduino is the same as using interrupts on any Arduino. The main loop counts interrupts over an interval currently set to 1,000 milliseconds. So it does that by first clearing the counts, count 1 and count 2. Notice this is occurring while interrupts are disabled. It then enables interrupts, and then this causes the main loop to simply wait for the interval to expire. After that, it turns the interrupts off again, clears the OLED display, and prints the counts. So this software is pretty simple, and the main takeaway is that everything's working in a standard Arduino way. But we can look at the system running and use an oscilloscope to look at the input and output signals, and also look at the counts on the OLED display, and we can get an idea of interrupt handling performance on the ATtiny. And by the way, I don't think I said it, but we're using an ATtiny 3224 today. That's a 14-pin device with more memory. And the reason that I wanted to use the larger ATtiny instead of the 412 with only 8 pins is that the OLED display is interfaced by I2C and needs 2 pins. So I didn't have enough pins and also didn't have enough memory on the 412. Hence we're using the 3224, which is a much more capable device. It has 32K of flash instead of 4K and 3K of SRAM instead of, I think it's 256 bytes. Here's a diagram of the system setup. The AD-ALM2000 generates square waves on signals IRQ1 and 2. This causes the interrupts. I'll put a link below to a video on the ATALM 2000. It's an interesting multifunction device. As we saw, the interrupt handler functions toggle the output on pins PB2 and PB3. We can observe all of this using an oscilloscope. Pins PB0 and 1 are the ATtiny 3224's I2C pins. They connect to the OLED display. Here's the setup on a breadboard. Note the 100 nanofarad decoupling capacitor soldered right onto the adapter between pins 1 and 14. Always use a decoupling capacitor with ATtinys. Place the cap as close to the ATtiny's VDD pin as you can. Here's my ATtiny programming device. The yellow wire connects to the ATtiny UPDI pin. I am using the 5-volt supply on the programming device to power the project. See the link below to an ATtiny introduction video that describes this. Next, let's see the system in action. The system's running. You can see an oscilloscope display at the top, and on the left there's the board, including the OLED display showing counts of interrupts. So you can see 1003, and that's the number of interrupts per second occurring on the IRQ1 channel. And then on the bottom and to the right, you see the controls for the signal generator. So going back to the oscilloscope display, the yellow trace is the IRQ1 signal. That's the signal that's causing the interrupt. And the sort of bluish trace is the pin that's being toggled in response. And we're triggering on the blue trace. So you can see that the change in the blue trace is always corresponding to the rising edge of the IRQ0 channel. And you can also see that the control is set to 1 kilohertz. And so we're seeing 1,000 interrupts per second in the count. So that's all working. So next I could enable channel 2, and then we'll see the next channel start doing the same thing. So now in the oscilloscope display, let's see, the magenta, kind of reddish magenta trace is the IRQ2 signal that causes the interrupt, and then the green trace is the pin toggling in response. And now you can see on the OLED display that they're both showing 1,000 interrupts per second. Now I want to use the oscilloscope controls to zoom in on the horizontal or time axis and get a better look at what's going on here. And then I'm going to do a single capture just to make it a little easier to look at. And I could use this cursor to point stuff out. So first we can see that the rising edges of the IRQ1 and IRQ2 signals, the yellow and the magenta-ish, are happening at about the same time. And that's because the signal generator is doing them at about the same time. And then you can see that there's a time lag between the IRQ signal rising edge and then the time of the toggle of the IRQ1 pin. So we can measure that using the cursors at about 6.24 microseconds. And notice that the toggle 2 happens after the toggle 1. So the green trace is changing state after the blue trace. And that has to be the case because the ATtiny has only one core. It can only run one interrupt service routine at a time. We might think that the second interrupt service routine, the one that's toggling the green trace, starts around here. And so that causes a time delay of about 2.3 microseconds, which is much less than what we saw for the first. So how can that be? It actually makes a lot of sense. So both of these interrupts are on the same port, and they're being caused by signals that are changing state and their rising edges occurred about the same time. So software that's part of megatinycore has to first save a bunch of context, save a bunch of state, and then it has to look at a register to see which port interrupts have actually been asserted. And then after it sees that, one at a time, it can run the interrupt service routines. So there's a bunch of extra context saving that has to happen before the first interrupt service routine can start running, probably around here. And then it completes it, and then it can run the second interrupt service routine. So the fact that the interrupts are occurring at the same time is actually making it easier to get high performance, but it's not very realistic. We really ought to try to shift the interrupts to occur at different times so that we can see the full cost of servicing both. We can do this by changing the phase of the IRQ2 signal. So right now it's at 0, and I'll change it to 355. And we can see that that moves the magenta trace over to the right. So let's do another single capture. And let's measure let's move this display over this way a little bit so we can see better. do another single capture. And let's use the cursors to measure again. So the time from the IRQ1 signal to the IRQ1 toggle is about 6.88 microseconds. And now let's measure the time. Let's put that back. So now measuring about 7 microseconds. So now let's shift this over and measure the IRQ2 time. And you can see that it's about the same this time. And that's because both of these interrupts are having to do all of that context saving. But the second interrupt is actually taking slightly longer, up to about here. And so that makes sense too, because the second interrupt service routine is using a less efficient way to toggle the pin. So this is also what we expect. These measurements are a little bit approximate because of the sensitivity to the cursor placement that I'm doing manually. How many interrupts can we do per second? Let's explore that by changing the IRQ2 signal phase to be 180 to make them just maximally separated. And we'll change the IRQ1 and IRQ2 rates to both be 50 megahertz. So there's IRQ2, and we can see in the count on the OLED display that IRQ2 is now happening 50,000 times per second. And now let's go to the IRQ1 and change it to be 50 kilohertz. And now we see something interesting. The OLED display has stopped updating entirely. It seems that we're taking so many interrupts that the main loop isn't being given any time at all. So let's try backing off, and we'll go to 48 kilohertz. And now the system comes back alive, and we can see that the IRQ1 interrupt service rate is 48,000, and the IRQ2 service rate is 50,000. But we're very close to the edge here, so let's set that to be 48,000 as well. And we see that the counts are correct, so it looks like the system's working. So now let's get the scope running again and adjust it to try to see what's going on. So I'll do a single capture and use these cursors again. Let's see, like so. So here we have the rising edge of IRQ1, and here we have the toggle point. So at some point after that toggle point, like in this space here, the context would be restored and the main loop would start to run. And so there's about, let's see, about this much space that might be representing time to run the main loop. And then that's also true for the second interrupt. So about from here to here, a little bit more of that. Well, I'm just guessing anyway, but that space there too. So you can see just by the scope display that we really are spending most of the time servicing interrupts when there's 48,000 interrupts per second per channel. So that's about the limit we can do with these standard Arduino interrupts. In this video, we've seen how to enable standard Arduino pin interrupts and showed that the interrupt processing rate is limited to around 96,000 interrupts per second. In my next video, I'll show how to handle interrupts more efficiently using ATtiny specific mechanisms rather than standard Arduino interfaces. I'll end this video here. Thanks for watching.